Today's session is going to be very important. Today, we are going to focus on uh, the embeddings. I mean, what is embedding exactly? We will try to understand it from the very basic, what exactly the embeddings are, and how we can use the embeddings. Okay, and how we can custom train the embeddings. Okay, on our data set. So those all practical implementation also we will see today that how we can perform. So we might have a few of the people have understood, or maybe they have understand that what exactly the word to I mean count vectorizer, like TF, IDF, all those things. Okay, but today we are going to focus on one specific algorithm which is called Word2Vec. Vec stands for vector. Word2Vec. So this algorithm was actually published by Google in 2013. Okay, and one more thing I just want to mention. There is one YouTube channel uh, name as Campus X. Campus X. Okay, and the name of that person is Nitish. I think Nitesh or Nitish. So actually, I learned the 99% or 100%, you can say, this entire thing of the word to it, how it can be trained from that video, from his video. So if you will not able to understand, or if I miss something, you think like that there isn't some gap, you can refer to his video also. I will add that video in the descriptions. Okay. So actually, he explained well, like any kind of techniques in NLP, whether it's LSTM, RNN, attentions, transformers, those are okay. But anyhow, I'm also covering it from the different. But this one, the word to wake is specifically I had learned or understood it from that video. Okay. So this is the YouTube channel name Campus X, and the name of that person is Nitesh or Nitish. Okay. So what exactly why we need embedding? So usually whatever the machine learning algorithms are there now, whatever the machine learning algorithms or the models are there, those were we cannot fade the text. We cannot fade the text directly to the model. Okay. So for that, it needs to be converted into the numbers. Just okay. So it needs to be converted into the numbers. The text should be converted into the numbers. Now, here the question would be, what should be the logical numbers that actually represent this text into a well manner? What should be the number? Or there is a way, either the number is sufficient, or do we need to represent this in a vector? Which one is better? So how to choose, how to understand? So those all things we'll try to understand. So there are few algorithms we need to understand. These are called what is called bag of words, BOW, and then TF-IDF. So these are just vectorizer algorithm. So these actually convert the text into the numbers. Okay. So usually how the bag of word works. So there is let's suppose the word sentence is there. Hello, how are you? If suppose this is a sentence. Now, how would I represent the hello? How would I represent the how, are, and you? Is there any way? So how bag of words simply works? So it will take all the unique words from your sentence. So if I'll take the unique words, there are something like whether you want the unique words with the stop words or without the stop words, or with the special character without. So usually the generic idea is, or the generic step is, you should remove the stop words and the special characters from the sentence, and then take your you just cleaned your corpus. That these are the cleaning steps. Perform something if you want to make it into the base form of your verb, like if you want to do the lemmatization, if you guys are aware of that or not. If not, I will cover that part also. Lemmatization is simply there are three forms of the verb. So your model will understand if any word is a verb of that sentence, and if it is in the base form of v2 or v3, it will make it into the form of v1. Okay, like good, better, best, like that it is, no. So it will make it into the base form if it is a verb, like that. So if suppose when we do cleaning, so we have these three words: hello, how, and you. So these are the hello, how, and you. The question is, how would I represent this word hello? So hello will be represented like this: 1 0 0. This how will be represented like 0 1 1. Sorry, 0 1 0. And this you will be represented like 0 0 and 1. This is a simple one hot encoding. So there are other algorithm as well, where you will take the count as well. Here I'm taking, if in that first sentence, if that word is there, so I'm putting it 1. So sometimes there is an algorithm like, if hello is coming 2 times, so I will write it here 2 in that sentence if it is coming. If how is, let's suppose in the second sentence it is coming here the 3 times, so I will take 3. In spite of giving the presence, we can make the count as well. So these are the way. Now, from these way, the TF-IDF is somehow better. So TF-IDF is term frequency and inverse document frequency. So how exactly it do? Let's suppose this is sentence 1, and here is in sentence 2, sentence 3, sentence 4, sentence 5. So the term frequency, what it will do, it will check this how many times this hello is available in this sentence. If suppose I have to create the number for this word hello, so first it will check how many times this word hello present in this sentence. And in the IDF, what it will do, how many times this hello word appear in this entire corpus, So if I will show you here the TF-IDF formula, TF-IDF formula with example. Yeah, see the frequency of term T in document D and total terms in document D. So this is the how you will calculate that. So frequency of term T means, let's suppose if you want to count, find it out the TF for the word hello. So how many times the word hello came in that document D, and the total terms, and the how many document D means that sentence, and the total terms in that document D. Okay, like total number. And the IDF is log we will take, and the total number of document, like how many total sentences you have, divided by total document with that specific word. So how many total sentence which contains the word hello, and then you will multiply this TF and IDF. So this is, you can see, TF and then IDF. Okay, so here someone has used any example or what? No example, but you will find it. I'll try to add any link. Definitely, I'll get it at the link that how exactly the TF IDF get calculated. Okay, so this is so. Now the question is how actually this Word2Vec, this the algorithm which I'm mentioning here, Word2Vec is different from this bag of word BOW and the TF-IDF. How it is different, that we need to understand. So the first point is here difference we want to see. So in Word2Vec we can get the semantic meaning. In Word2Vec we will get the semantic meaning. I will also the practical implementation as well. So the semantic meaning means we can perform the similarity between two words, like if uh, is there any similarity between the king and the monkey? What is the similarity score between this one and this one? We can do. We can understand. Let's suppose if I'll give an example, we have a three words: king, uh, male, queen, and okay, three words. Now, if suppose the king had some value, some numbers in a vector, this word male has uh, some number, and this word queen has some number. Okay. Usually, king and male should be more similar in terms of which feature? In terms of their gender. But the king and queen are also similar now, in not in terms of the gender, in terms of the royalty, because the both are from the royal families, both are rich. Okay, so this is how the similarity works, how the feature gets generated in that algorithm. I will come on that how the feature manually I will try to generate, and we will see that in the algorithm how it will get generated. But the one more best thing we can do it here, like if I will subtract king minus male, so whatever it means that I'm subtracting the vector of king minus the vector of male. So I will get one vector. So probably this vector will be more similar to the vector of queen. How? Because from the king, I am just trying to extract the male feature. Now, in between king and queen, there is an one difference only with respect of that major difference with respect of the gender, and that gender features I'm trying to remove it from the king. So it means whatever the vector I will get, that will be the more similar to the queen vector. It will come. It will not be 100%. The reason behind that, there could be the multiple features which are differentiator, like king is maybe because of the male dominant society, king might have the some, if there isn't some feature of like uh, cruelness or the rudeness like that. So in those part it might may some still the difference would be, but the majority difference will get removed, and the king vector, this vector will become the similar to the queen vector. So this is how. Now in bag of words or the TF-IDF, the dimensions are too high. So semantic meaning means, if I'll ask a simple, just do not understand a Word2Vec or any algorithm. If I will ask, is there any similarity between the word king and queen? If I'll ask that, give me three similarities between king and queen. So what those all are? Tell me. Definitely you can say those are, both are richer, rich, okay, rich, royal family, from the royal family, you can say. Well, any other thing like that you can think. So these two are the similarities you can say between these two. So that's the semantic meaning. Semantic meaning means how, on what features actually are you differentiating between the two words, or on what features or on what basis you are separating or discriminating, or you are saying that these two text are, or two words are not similar. So there is an one parameter is the which is get making them both a difference, which is called gender, which is male. So king is male and the queen is female. That is the differentiating factor, making their uh, presence difference from each other. King might be more dominant, queen is lesser dominant. Usually it happens in the male dominant society. So that these all things will get captured in Word2Vec. I'll tell you that how Word2Vec will capture these all. So that's what I showed it here. I try to explain it from the vector. Okay. Now I'll come on this again. Now in TF, IDF and Word2Vec, what happens? Let us suppose you have a huge corpus and with the unique word is like 10 lakhs, 10 lakh. So in that, what will happen? The first word will be here 0, or let's start it with the 1, no, so that it will be easy to write, and the 10 lakh. Now if suppose there is one word hello and it presents on the index 736, so here it will be 1 and rest entire thing will be the 0. You can see, and you can see how bigger this dimension will become. This dimension will become for the word hello, how huge it. So this is the problem with the TF, IDF and Word2Vec. Their dimensions are too high, and not only the high, their majority values are 0. Okay, which doesn't have any much information. Means this word hello is not saying any information about the word which is at the index 1. It is not giving you. In TF, IDF it gives, but it will not cover the context more. Okay, so this is the issue with the, this was the issue with the TF, IDF and the back of word. But in Word2Vec, this you will see this all the numbers, these all numbers are non-zero. It will never be zero. Almost 99.999% of time this will not be zero. So there will no issues of the overfitting. But in case of the TF, IDF and the Word2Vec bag of word, there will be the higher chance that your algorithm will get overfitted, because it is very hard coded. It is saying this one is related to this one. The rules are straightforward. That's why it become, maybe it will become the overfitted. With some result it will give the best performance, and with the little bit, if it will get changed in the context of hello, there it will fail or it will give the high error. Okay, so this is the problem. Now how we can use the Word2Vec? This is the question. How we can? So there are two ways. Either you can use pre-trained model of Word2Vec, or else you can custom train the model. You can customly train the model. Now this Word2Vec was actually developed and trained by the Google team. So Google has actually trained the model on Google News corpus. So Google News, if you'll go on a website of the Google News, there are daily news getting updated, so the corpus were there. So they took the Google News data, Google News data, and how much it actually took? 3 billion. 3 billion. So 3 billion is how much? It is 30 lakh, right? So 1 billion. So the Google has used on the 3 billion, and the dimension for the every word was 300. Okay. So this is the train. But we can do the custom training as well. We can perform the custom training as well on our data. Now the question is, why it required the custom training? Okay, so let us suppose in a Google, if they have used this 300 lakhs or the 30 lakhs, I'm a little bit confused if it is a 3 million or the 3 billion. Okay, so whatever it is, I'll have to cross check. So if suppose, let's stick on the 30 lakh if it is million. So if the 30 lakh word you are using, And let's suppose you are working on your custom work, and if these words are not available on in your task, at that point of time, this pre-trained model will not able to generate the vector, or else it will generate the vector with very less or wrong information, with the wrong context, or with the very less informed context. Okay, so this is how it works. So let's see first the custom trained model, how it work. Okay, so see, so this is there is an one library you guys must have to install, which is called gensim, and I'll share these codes. There's nothing by the way, it is too easy. And from gensim I'm just importing word2vec, and here I had taken the sentences in a tokenized format in a word, like this is the first sentence for word2vec, and this is the second sentence, this is the second sentence, yet another sentence, one more sentence, and the final sentence. And in word2vec I am passing this sentence. So sentence is a list of the sentences. And minimum count is what? If I give one, means it will create a vector for those word only which has at least the one, the minimum count is one, that frequency is one. If I'll pass it 4 or 5, by default I think it is 5. Yeah, you can see the minimum count is here 5. It means that if any of the word which are less than the 5 number of times, it will not consider that word, because since here the corpus is very small, so that's why I had put it as a 1. Now this model is created. Now this is your word2vec model on this task. So this is not a trained, this is a pre-trained. So these all words are already available in this word2vec, so I gave these all words, and it has just generated. And now if you want to check that for any word, so see here list, what I did, model.wv and key to index dot keys. If you will do, it will give the entire thing. Let me yeah, see this. So let me first, okay, this one. So let me run this now. See. So here two things I'm printing, this word, and then I'm printing the words here. See. So when I'm printing the model, see this is the model with vocab size, it is saying 14. Vector size by default, the vector size is 100. Alpha is the one value, I will come on that. And this is the words, this is the entire words available. Now if I want to check what is the vector of this sentence, okay, what is the vector of this word sentence, which is here we have used it. So now let me run it once more. See, this is the vector. So these are from the pre-trained, and here I have used shape. You can see it is 100. So I told you that they have used it on the on a dimension of 300. So here you can use here the dimension. I think it will be. Let me check here the dimension. Vector size is by default 100, but if you will pass here 300, it will generate with the 300 as well. See that it has generated with the 300. Okay, so there are two models actually. They are trained on 100 and the 300. So this is, so we can check the similarity as well. Let me open for you word2vec similarity. So this is actually a downloaded model from the Google. Their vector that it is, I actually deleted that. So I'll show it from here. Don't worry. Let me go in a custom. Let me add some here. So from gensim dot models import, I have to import the word2vec, and then key d vectors. Okay. Now, so actually it will download the model. So let me first use that vectors dot load Word2Vec format. Okay, fine. That one I need to download. Actually, this one I have to download it from the outside. Wait. So it need to be downloaded. Where it is before I want to where it's so you can see it need I have to download this. Once I'll download, you can directly use that. So I do not want to go there, but I'll share the link. You can use that. So once you will download, no, you can perform the similarity. See that here I have done king minus man plus woman. So what it will be, and here you can perform the similarity like model dot most similar word. Positive is the woman and king, and the negative is the man. So what exactly it will come? I'll put it into download and let move ahead, and we will see that how we can. So this all functionality I will show on the pre-trained. Otherwise, I have to download it. So that's not. Tell me one thing. How many of you have watched the Game of Thrones? You guys have watched that series or not? That Game of Thrones? Okay. So do you guys remember any of the character names from that? This one, remember? Recon, Rob, Arya, Sansa, Bran. Oh, okay, okay. Then, so I had actually taken that data from the Kaggle, uh, and I have done the Word2Vec embedding on that on Game of Thrones. So I'll come on that. Let's see this. So now here the question is why we needed. I mean, we understood that why the pre-trained is there and why we needed a custom training. So because of on our data, if whatever the words are there, those were not available in the pre-trained, in those scenarios we have to customly train the model. Now how would we custom train the model? Please focus this, because if you will understand this, that how the embedding works, this is going to give you a pillar, a base to understand the generative AI part. Now, so the first thing, suppose we have total 5 words in our corpus. So I'm taking very small uh, example, and that is again I'm taking the same example in the campus X that person has taken, the Nitesh. Then the second thing, now we need to create a vector. The second is we need to create a vector of these 5 words which can capture the meaning of the words, capture the meaning of the words. And the third is the most important, this word2vec, this word2vec algorithm, actually word2vec creates the features. Now how it will create a feature, I will come on that. What is the feature? Those all things we'll try to understand. So first let's build the data set. The 5 words are, let's suppose king, queen, man, woman, and monkey. These are the five words. Now, here, here I will write the features. So the feature is, let's suppose the first feature is gender. I mean, I want to represent these all five words on basis of the one feature which is called gender. The other is the wealth. Wealth is that like how rich or like that. And the third is power, how powerful. And the fourth is weight. And the fifth is, let's suppose, speak, whether they can speak or not. So these are the five features. So randomly, I had just taken randomly. Okay. Now so the king is definitely, let's suppose male is representing as a one. So king is one. If suppose definitely king is male. So the queen will be zero. It's a female. Man is a one. Woman is again zero. And if suppose the monkey is here is the male monkey. So it will be one. Okay. So this is the first done. Now the wealth wise. King is if richer, definitely one. Queen is also richer. Let's suppose this man is not that much richer, so we just make it 0.3. Woman is not that much richer, 0.3, and let's suppose monkey is not richer, so 0 on the monkey. Power. Definitely, king has the more power. Queen is little bit lesser power than uh, king, 0.2. If suppose man has and woman has a lesser power, so this 0.2, 0.2. The monkey doesn't have any power. So I have put it as a 0. Weight. Let's suppose the king is having zero point 0.8 and the queen is little bit having lesser weight, so 0.4, and the man has little bit higher weight somehow than the queen or lesser than the king, so 0.6, and this woman is the lesser one, 0.5, and then this monkey has a very less weight, so 0.3. Now speak. So definitely king can speak, queen can speak, uh, man can speak, and woman can speak. But monkey, I'm saying they can speak, but I'm talking about the human languages, that human language. So in that case, the monkey, I have denoted it as a 0, that monkey cannot speak. Now here, by seeing this data, how I will represent the, what is the vector of the king? So the vector of the king is 1, 1, 1, 0.8 and 1. It means now I am representing the kings in terms of these features. Feature 1, feature 2, feature 3, feature 4, feature 5, or maybe feature n. It could be the multiple features. So this feature is called dimension size. Dimension size. What is the vector size, or what will be the dimension of your embedding model? Which I was saying, no, that Word2Vec was with the 100 dimension and the 300 dimension. It means in one of the Word2Vec model, they have created the 100 features to represent the every word, and in one of their model to represent the specific word, they have used the 300 features. So now you can understand it, or you will have the intuition that greater the features, better the understanding of this word. Means if you'll have any sentence will come where the king has written, and if it will be context related to that feature, then you will have the better understanding, right? So higher the feature, higher the embedding size of the specific words of the model, uh, better the embedding model is. Okay. So here, whatever the features I have taken, those are on the basis of the just an intuitions. The randomly I have taken the words and the features. Okay, and definitely the queen vector will be like 0, 1, 0.7, 0.4. So these all are the vectors, and the vector size is same for all because it is from the word. Now, word to wake, what exactly when you train the model? No, so word to wake, what exactly do? Word to wake, word to wake tries to create features on your vocabulary. Now, why I'm saying this? Here it was I had created the five. I have to write the five features so I can do. Let's suppose you have to think 100, and how would you think the 100? Because here I thought five relatable because of I know these five small words. But let's suppose you have in your corpus there are 4 lakh words. How manually will create these all features? That is really not possible. Okay. So in that, what will do the algorithm, the Word2Vec is actually a neural network algorithm. Okay, deep neural network, shallow is only one hidden layer. That is what, and they create this feature automatically while training. Okay, so in our case, we have only the 5 words. By when we need to train the model, then we cannot create these features by our own. We have to build some automated way, that is again we generate it into the Word2Vec model. So these features will get generated into Word2Vec automatically. Okay, we do not have to manually do. Now, so and it can be done by the neural network again. That Word2Vec is a neural network at the end, but we will not. The one downside you can say, or one demerit you can say, here you are seeing the feature, but when you will train the model, no, you will not able to see that what features actually it has generated. Okay, so that is the problem, but we do not have to worry about that. We'll have to just understand that what is exactly the embedding vector and whether it is correct or not. Okay, so you understand till here? Any confusion, any question? Now, the next thing we need to understand the types of Word2Vec. Types of Word2Vec. How many different types of Word2 vectors are there? Okay. So there are two architectures of Word2Vec. These both are similar. There is little bit change. So the first is CBOW and other is skipgram. CBOW is continuous bag of words. Continuous bag of words. This is a full form for SIBO. And skipgram is nothing full form. Now we need to understand what is the difference between that, what is SIBO and what is that. So I'm taking this text again, it from the same video, that the text is watch Campus X for AI. Okay. If suppose this is the one sentence. So when I'm saying that the Word2Vec is a neural network. So when I'm saying this Word2Vec is a neural network, then we must have to train a neural network. We must have the data. So how it can be done? So first we need to prepare the training data from the text. Let's suppose I have this text. It could be the multiple sentences like millions, billions, trillions, whatever. But just for a smaller and to understand it intuitively, we have this one sentence, watch Campus X for AI. Now from this, how would we generate? So there are two things we need to understand to create this SIBO neural network. The first is window size. There is sliding window, vector dimension. These two, three things are important. Now, if suppose the window size is 3, so what exactly it means? If window size is 3, it means this will be the 3 words I will take, and this word, the center one, will be the target, and this both two will be the context word. Or in a more simpler way, you can say this is the y and these two are the x. And now the sliding window is if suppose 1. So what it will do, the next time it will take these three sentences. Then this one will become y and this one will become x and this one will become x. How the data will look like? Data will look like somehow this. If this is your x, this is your y. So the first time the was watch and for, and the y is Campus X. Second time Campus X and AI, and the target is 4. Getting my point? Now we have X and Y. We will train the model, but still these are the text. So this how would we convert into? So this watch and for, these all we will convert by using the one hot encoding. So if this is a sentence, you will have the one hot encoder for the watch, for the Campus X, for the for, and for the AI. You will have that like 100010 like that. So let me create it for you guys so that you will understand more better. So here I will create. So first create the Word2Vec this one hot encoder for you. Watch Campus X for AI. So for the word watch, this is 1000. Campus X, this is 0100. For 0010, and for the word AI 0001. So this is the one hot encoded you have. Now we have the data for the watch. This is this vector. Sorry. 1 second. Watch, you have this vector, or here in this case, but actually it is no here in the scenario this one. Okay, and then this one, this one, this one. Now, so for the watch, you will place this vector, then this vector. Now, how actually the SIBO look, the neural network. So let me tell you. And very carefully you need to understand this. So how many total words? So I have total 1, 2, 3, 4 unique words were there. So this is the network with the nodes 1, 2, 3 and 4. 1, 2, 3, 4. Here also 1, 2, 3 and 4. 1, 2, 3, 4. Okay. And now here is the hidden layer. And here this one, how many neurons will be here? It will be on your window size. So we had taken a window size is 3. Window size means now we want the dimension. Window size means not here it means that what dimension I want. Means like Google has the 300 dimension for every word, but I want the 3 dimensions. So that will be the 3 neurons here. Then after your final layer, so in the final layer, you will have how many unique words, that much neurons here. And this is a dense neural network. So the entire neurons will be connected to each other. So I'm just writing it like this. So this network layer with this one. So here, let's suppose the first word is coming watch. And what was the, let me check what is, right, a watch and for, 2 words. So 2 words is coming watch and for. So what is the encoding for the watch? It is 1 0 0 0, and for the for it is 0 0 1 0. So 0 0 1 0. Okay, and this is also connected with here to here. So what will be the dimension of this? This is here 4 and this is 3. So this dimension is 4 cross 3, and this is also 4 cross 3. And this one will also connected with the output layer. So this dimension is 3 cross 4. And here we will have the softmax activation function. This one will represent as a watch. This one is a campus X. This one is for, and this is for the AI. So definitely it will assign some value like maybe 0 0.2, 0 0.3, 0 0.1 or 0 0.4, like that. So, but for watch and for, what should be the label? The label should be the campus X. So here the higher probability it has given to the AI. So it will do the back propagation, and I mean it will calculate the loss, do the back propagation, it will go and again come back. The how the neural network works, and this is the how you're embedding. Now you understand this is why I had taken a 4, because it is on the your unique words. This one why I had taken 3, because we had decided the dimension should be the 3. Okay, 3 as a vector dimension, that everyone. Now here you might can ask, then where is the embedding vector? So the embedding vector is actually this one. Like when I'm saying it here, this every word, this one I have written, just let me create a new figure for this part only, for this part. So here this is 3 and here it is 4. Now, and this is for the word watch. So this watch word is connected with this one, and this one. So this there is an 1 value, 2 value, 3 value for this word. Again for the word campus X, it will be 3 different values, no? Same with the other word. So for the every words we will have the different vectors, and what will be the size? 3, because 3 values are coming for every one. Let's suppose you want it to the 5. So in this layer you will increase. So your dimension will get increased for the every word. Okay. Now let's understand the skip gram. So skip gram is, you just understand it is opposite to the SIBO. So in SIBO, continuous back of what we were trying to do, we have the 2 context words and we were predicting the target. We were doing it like that. But it is just opposite into skip gram. Skip gram will have a target as a X, and in Y it will have the context word. So this is the what we need to prepare the data in this manner. Just you have to reverse the data simply. So because of this, the architecture, so the same data you can just understand this one will become the x, this one will become the x, and this one will become the y for the skip gram. And for this the architecture will look like this. So here I'm saying the target is one word, so definitely here only one, and the input here neurons is 4 because there are total unique 4 words are there. And then here in center, if suppose I want the dimension with 3 vectors for every word, so that will be 3. And at the end here there will be, because we need to predict the two context word. Now if suppose there are window size is 3, so 1 2 3 and 4 here, 1 2 1 2 3 and 4 here. Now if suppose the first word is going here, the campus x, because it was the target, you can see it here. See, this is the target. So if suppose the campus x is going, so what is the vector of the campus x? 0 1 0 0. So here 0 1 0 0, it is going here. It is again a dense neural network. This is connected. This is dense neural network. Here it is. It will be connected. It's the dense neural network. Here it is connected. What is the dimension here? 4 cross 3. Here 3 cross 4. Here 3 cross 4. Now in this skip gram, this is your embedding. And see what will be the size. So for every word here, how it will be generated, there are 4 with the 3 features, row and column. So the every word will be get generated. Now if you will increase this every word will get generated in the higher dimensions. Okay, so this is how exactly it works. Now there are one thing which is very important and we need to understand, that how we can improve in interview. They might ask how would we improve the performance of the Word2Vec. Okay, uh, or maybe why we are using this difference if both are same, SIBO and skip graph. So there are some research paper in which they have claimed that if you have a smaller data set, in that the SIBO works well. If you have the smaller data set, the corpus is small. But if you have the huge data, in that you can go with the skip gram, it will perform well. Okay. Now the question is how we can improve it. So the first thing, to increase the training data, the performance will get increased. By increasing the training data, performance will get increased. Second, if we increase the dimension of the vector, which I already told you, like here we have taken example for 3, let's suppose 100, 200, 2000. I'll show you in the embedding vector that in transformers or the large language model, that what are the dimensions, how huge, like 88,000 dimensions are there now. A dimension of vector, if we will increase. And the third is window size. Like window size, we know the context length actually, that is. So the window size here 3, so 2 are the only. If suppose if I'll take the window size as a 5, so this is the target what is the center, and the 2 here and the 2 here. If suppose I had taken 7, so 1 2 3 1 2 3, the context length will be higher. So if you will increase the window size or the context length, window size or context length, so it will understand. Oh, for this word now it is going to learn it from these 3 words, from the behind and from the forward as well. So this is how it works. Now let's jump to the practical implementation, that how we can train it. Okay, so you can see this, I have here that now. So this is the just I have imported this file, and here I have this data, Game of Thrones data. So this is from the Kaggle again. You can open source it is. You can directly download it. You can on a Kaggle if you will type, or else I will add the this link in the description. You can download the data from there. And here what I'm just trying to do in this line of code, from this data folder, I'm going through each text file one by one. You can see it here. I'm just using Latin encoding. It was throwing error, and I'm reading the each file in a corpus. And then from the sentence tokenizer I have used here, from the sentence tokenizer I'm tokenizing the sentence, and from the every sentence that I'm appending into this list. Okay. Now here I'm doing simple pre-processing. There are a lot many pre-processing can be done, like removing the stopwords and all those. Okay. So this is I'm just performing it here. Okay. Now, why it is taking, yeah. Now this is in the story. If you will print just here 0, so this is the first sentence. Or if I will just give you the, so this is the, like, the wildlings are dead. So this is the sentence. These are like sentence 2. So if you want to see the how many total sentences are there, so 1,45,020 sentences are there total it has generated. Now we will create and train our own model. So here I am creating the model object. See this GenSim we have imported above. GenSim is the library by which we will have use the Word2Vec. GenSim.models to Word2Vec, and these are the few parameters. Window size I am taking here 10. Minimum count, at least that word should be the 2 times. You can increase. This worker is about your CPU, that how you want to make the load on the CPU. Vector size, that what I said, the dimension of your vectors, how much you want, 100, 200, 300. Epoch, you might guys have aware that for how many epochs you want to train. So by default it is 5. That's why I taken only the 5. You can increase it, but this is just for a demo purpose. So we have generated. Now, so we will build the vocabulary for our model. We pass the entire this list in that, and this is the epoch. We are just checking it, nothing, because I have given. Now here simply we'll have to train. So we'll have to pass the story, that entire corpus, and the total number of example. So total number of example you will get model from corpus count. So actually it will give this one, the corpus count probably. Let me run this model.corpus count. So it will give this much only. Yeah, this is the total corpus count. Okay, and the epochs in a training, because model.epochs how much it was, that I have passed. And let me train this. It will take not much time probably, but I have trained that. Yeah, so 4.8 second. Now it has given this. It has trained. Now how to understand? So if you guys have ever watched or know about the Game of Thrones, here in a model there is a WV, like word vector, and there is an one method or function most similar, and you can pass the sentence. So according to your trained model, it will give you the most similar. So for the Danius, it is saying it is more related to the Stormborn by 78%, or the probability of 0.78. With Tagran, it is 0.78 again. Like that, it has given. Okay, and if you want to check the vector of the words, you can see this like that. You can check. You can see here I have passed the in a list of the multiple characters from the word from the that, and the sentence is here, the method is here doesn't match. So I pass the list of character and I want to see which is doesn't match from this. So it has says that John is not matching with this entire so this is the John is somehow different. If you want to check the similarity, you can do here, like similarity between Arya and Sansa. So it is saying those were related to 85%. Why? Because I think the both were the sisters, if you have watched or know about the Game of Thrones. So that's why it is saying it is 85%. Now Cersei and Sansa, when I'm checking, it has still given the 75. The reason, because the both are related from the royal family. But when I checked it with the Tyan and Sansa, it is saying the 28, because those were not related to each. Okay, so this is how exactly you can train your model and you can utilize that. And if you want to save your model, this is the way, like model.save, model.bin. This bin file you can save. Okay, and anywhere you can use that. You can send it to the customer anywhere, that this is the model file. You can utilize it to generate the embedding to understand. And here let me see that whether it has generated. I was showing it to just to do the visualization, but that's fine. That is just an extra I had. So this is the process that how you train a custom model. Let me show you one thing which you guys might relate, you will understand. So I'm just showing that MTB leaderboard, which is embedding model leaderboards, whatever it is getting released nowadays. See that. This is the embedding model, SFR embedding Mistral. Mistral is an organization, they were releasing hugely in the GNAI. So model size in GB is 14 GB. This embedding dimension 4096. Embedding dimension means for every word, the number of vector is 4096, in which we were taking 100 or 300 or maybe 3 in the rough example. Max token, this is the context length for the every word, that much of the huge at a one time it will able to understand. 32,768. See how huge it is. And they have given average on 56 data set, the performance, classification average, clustering average, that how we can do the clustering as well, re-rank. Those all are what retrieval average, how to retrieve the information. So those all it has given. So like that, there are multiple models are there. You can see this is the leaderboard. Okay. So this is how you can, and if you want to use according to your task, let's suppose I want to use it, so you can sort it on basis of your task as well. Okay. So this is how embedding works. And now what to week was for now a scenario. In today's scenario, it is very simpler. We need to understand this how transformers in these language models or the embedding models are getting trained and built. Okay, those things we need to understand. Okay, okay. So this is the part. Now